Hello, this is Dr. Webb, and welcome to this calculus video where we will be talking about continuity. So what continuity means is that the value of the function is equal to the limit of the function as you approach it. So we say that a function is continuous at a value x equals a if the limit of the function as x equals a equals the actual value of the function. Now if you think about it, this is what we really want to have happen. You know, anytime that we don't have something continuous, it means there has to be some sort of break in the function there. Things have to kind of break apart in some way. And then in general, that's what kind of gives us, you know, quote unquote kind of ugliness to some degree of functions when they don't connect up completely. And so the idea of continuous is that if the value of the function there matches up to the limit as it goes in, things kind of travel nicely connected together at that point. So we've already actually shown that a lot of functions are continuous. We just haven't been using this terminology yet. Right? So what are some functions that we've already talked about being continuous? Well, one is just a constant function. If f of x equals c, well then everywhere the limit as x goes to a of c is equal to c, and so that's still the value of the function. F of x equals x. We showed that in the last video, that the limit as x goes to a of x is equal to a. And so that's the same thing as saying that it's continuous there because the value of x at a is a. In fact, in the last video, we actually showed that all polynomials are continuous for all values a. And so anytime that we have a polynomial, this is going to be continuous. Okay, so now let's suppose that we have two functions, f of x and g of x, that are both continuous at x equals a. So remember, continuous, this is saying that the limit of f of x as x goes to a of f of x is equal to f of a, and the limit of g of x as x goes to a is equal to g of a. And so really what's important is that these are really our two statements about values of limits as x goes to a. And in the last one, we were talking about limit rules. We talked about a lot of arithmetic we can do out of that. And so we can, since talking about continuity is really talking about limits, we can apply the same arithmetic rules to continuous functions that we did for values of limits. So the following functions are all going to be continuous at x equals a as well. Well, what were the rules we could do? Well, we could add functions together, we could subtract them, and we could multiply them, and the limits all work out the way that we want them to, and so that's going to mean that these functions are all continuous as well. So anytime you can add continuous functions together and get something that's continuous, you can subtract continuous functions from each other and get something that's continuous. And we can multiply continuous functions together and get something that's continuous. The other rule that we got is that we can divide two continuous functions and get something that's continuous so long as the denominator is not equal to 0. And that comes from this rule that we can take the limit of two functions, f of x over g of x, so long as the denominator is not going to 0. Well, what are rational functions? Rational functions are just one polynomial divided by another polynomial. And so this last rule tells us that rational functions are going to be continuous whenever the denominator is not 0. And so really this means that rational functions are continuous whenever they are defined on their entire domain. So long as their denominator is non-zero, this means their entire domain. Anywhere that you can plug in values and get something of meaning, it's going to be continuous there. Right, so let's use this, work out this limit of this rational function right here. So we have x squared plus 4x minus 2 over x squared plus x plus 1. We're taking the limit as x goes to 2. Well, let's check the denominator at 2. So if I plug in 2 squared plus 2 and then add one more to that, that's going to be 4 plus 2 plus 1 is 7. 7 is definitely not equal to 0. And so that means that the function is continuous at x equals 2. And so all we need to do is just plug 2 in for x everywhere. So it's going to be 4 plus 8 minus 2. We already figured out that the bottom is 7. So I have 12 minus 2 is 10 over 7. And we're done. Okay. There's one more thing that we can do with continuity, and that's play around with function composition. And so this is what I mean. So let's suppose that we have a function f of x that's continuous at x equals a, right? And so this part right here means that the limit of, as x goes to a, of f of x equals f of a. And then let's suppose that g of x is continuous at x equals f of a. So the important thing to note here is that the x value for g of x is coming from the y value of f of x. And so this statement here, g of x is continuous at x equals f of a, that means that we take the limit of g of x as x goes to f of a. Well, what do we get out of that? Well, we'd be taking the x value that we're going to, which is f of a, and then plugging it into g at that point. So the limit of g of x as x goes to f of a would be g of f of a. Well, what we can do is we can then take the composition of these two functions. So g of f of x is equal to g of f of x is also going to be continuous at x equals a. Right? And so, before f of a of g of x is equal to g of f of a, well, really all that we're doing here in this statement is we're replacing this limit here. Instead of doing g of x, we're doing g of f of x. And then instead of x going to f of a, x is just going to a. And we're saying that we're still ending up with g of f of a. Okay. So this is going to be very helpful. So this means that anytime that we have two continuous functions, if we plug one continuous function into another continuous function, then we still have a continuous function at that point. So now we're going to talk a little bit about invertibility. So we say that a function f of x is invertible if we have an inverse function, which we're going to call f to the minus 1 of x. So this is different. This is not equal to 1 over f of x. We're not taking the reciprocal of f of x. We're doing we're using what's called the functional inverse. And so what's true about this f inverse of x? Well, for all x in the domain of f of x, if we then plug f of x back into the inverse, x spits back out. Okay. And so if you think about what this is saying, right here, this is talking about plugging f of x into f inverse and getting x out. And so what this means is that if x f of x, this would be a point on the graph of f of x. Well, then we would have that if we swapped the x and the y values, so if we plug f of x into f inverse, we get x back out. So that's saying that the point f of x, comma x, is now a point on the graph of f inverse of x. Okay. So let's talk about what we mean with invertible functions. So start off, this right here, this is a graph of y equals x squared. Okay. So if we want it to be invertible, that means that we need to find this inverse function, and it has to be a function as well. So remember that for f itself to be a function, that's talking about the vertical line test, that if we took vertical lines, they're only going to pass through the function at most once at any point. If we want it to be invertible, that means that we need to be able to swap the x and the y values and still get a function, right? Well, that's thinking about what's called the horizontal line test. And for y equals x squared, this isn't going to work, because if I take some y value bigger than 0, it's going to cross the parabola twice, right? And so this is not a function swapping the x's and the y's. And so what do we need to do? Well, we're going to need to get rid of 1/2 of this parabola, and that's going to get rid of half those, the other side of values that we're crossing through. So to make f of x invertible, we're going to ignore, basically drop off all of the negative x values. So we're left with just the right half of the parabola. What we did right here, this is what's called restricting the domain to all x that are greater than or equal to 0. And so by taking away the part of the domain where x is negative, now when we do horizontal lines across, we're only crossing the function once. Okay? And so now we can swap the x and the y values and end up with a function the other way. So how exactly does that work? Well, swapping the x and the y values, this is equivalent to flipping the function over the line y equals x, right? And so if we took any point on here, x comma f of x, it's going to get flipped across this line to a new value, which is going to be on the inverse, f of x comma x. And so we're going to do that with all these values. And we get this new function. And this function just happens to be, how do you undo squaring? Well, you take the square root of that function. Okay, and so at the end of this, we end up with, if I take the square root of x squared for any x greater than or equal to 0, well, the square root and the x squared, in this case, they cancel themselves off. I end up with x. And so this is equivalent to saying that if f of x is x squared for all x greater than or equal to 0, restricting the domain, then the inverse function is the square root of x. Okay. And so what's important about this in terms of continuity is that if f of x is continuous, so when we draw it, it connects up together nicely, doesn't have any breaks in it, well then when we flip its picture, when we flip its graph over the line y equals x, it's still not going to be breaking apart at all. And so that means that its inverse is also continuous. And so this means that whenever we have a continuous function the inverse to that function is always continuous. So what's that going to mean? Well, it means that now we can say all of these functions are going to be continuous. So we already saw that linear functions, polynomial functions, and rational functions are continuous, so long as we're thinking about all the x values where they're defined. Okay, but now we can talk about taking the inverses of these functions. And so the inverses of these functions give us what are called the algebraic functions. And so these are functions involving square roots, cube roots, any types of roots you want, mixed in with polynomials, rational functions, etc. We can also take compositions of these. And so since we have that x squared plus 1 is continuous, and now we know that square root of x is continuous whenever it's defined. So here, square root of x is defined for x greater than or equal to 0. Well, that means that I can take x squared plus 1, plug it in to square root of x. For any x value I plug in here, I'm always going to end up with something positive inside the square root. And so this new function that we got from the composition, this is now continuous for all x values. There's more we can do than this. So exponential functions, so this is functions like y equals 2 to the x, y equals e to the x, y equals 1/2 to the x. These are all continuous functions. In fact, without getting too deep into the weeds, these are actually kind of defined to be continuous functions. These are forced to be continuous functions. And then what happens when you take the inverse of an exponential function? Well, that's when you get logarithms. And so exponential functions are continuous. That means that logarithmic functions are continuous as well. That is all for this video. I will see you again soon.